Okay. Hi, and welcome to this lecture on mechanics. Today, this lecture hall looks like a physics laboratory because many experiments have been set up here for demonstration. In other courses, some optics experiments and electricity. And also in this hall, we have lectures on thermodynamics. So when you will learn thermodynamics and electricity and optics, you will see a lot of demonstrational experiments in this lecture hall. And we today continue our mechanics. And today we start Newton's laws, a well-known topic. It should be said that the first attempt to treat forces and velocities from scientific point of view was made by Aristotle more than 2,000 years ago. Aristotle lived more than 300 years before Christ. So he established that the velocity of a body is proportional to a force acting on this body. This was written by Aristotle, and for about 2,000 years people believed that was correct. And actually, such a dependence between force and velocity relies on observations, and this relationship is in good agreement with observations, because if you have a cart which you have to push, if you push slightly, the velocity will be small. If you want to increase the velocity of the cart, you have to push it stronger. You have to apply larger force. Quicker. And the same goes to a boat on the surface of a lake. If you are in a boat and you row with your paddles, if you apply small force, then the velocity of the boat will be small. If you want your boat to move faster, you have to apply stronger force, a larger force, while rowing. So this relationship is based on observations, and this relationship is and was believed to be in agreement with our world, with real world. It took about 2,000 years to understand that this is not quite correct. Aristotle, who wrote this relationship, was a great scientist, a great thinker and philosopher. And by the way, he was a student of Plato, another famous and outstanding philosopher of ancient Greece. But Aristotle did not follow fully the philosophical approaches of Plato. Aristotle criticized him in some aspects, and Aristotle developed his own philosophical concepts, which do not coincide fully with what Plato taught his students. And among the students of Aristotle himself was Alexander Macedonsky, by the way. So all that was more than 300 years before Christ. And for 2,000 years, people believed that was correct. It took 2,000 years to understand that something is not good in this formula. And the first person, the first scientist who endeavored complicated and many experiments to check this formula was Galileo Galilei. So that was, according to Aristotle, and something was changed in this formula by Galilee. It's well known what Galilei did. He dropped heavy bodies of objects from a Pisa tower, a tower in Pisa, in Italy. That is a leaned tower, which is, well, convenient, which was very high, the highest building in those times. More than 300 years ago, Galilei dropped different objects from the Tower of Pisa, and he found that the time was the same for all the objects to reach the surface ground, the surface of the Earth, to reach the ground. It took the same time for different bodies having different masses. That was very interesting. If you take a heavy body, it falls in the same way like all other heavy bodies. If you take a light body like a bird's feather, it flies down very slowly. But any heavy body goes down at the same time. It takes the same time to hit the ground. So Galilei was not quite satisfied with his results, because it takes very small time for a body to fall down. And so he devised an experiment which allowed him to investigate this phenomenon in greater detail. And the experiment was Galilei's ramp, or inclined surface. He rolled down balls down the inclined surface, and he measured time which is required for the ball to reach the base of this inclined surface. He measured time using a water clock. Water clock is very much like a sand clock. You have to measure the amount of water flown in order to calculate the time interval. So you open the valve and water starts flowing down, and you take this water in some vessel, in some glass, and then when the process is over, you close the valve, and then you have to measure the mass of this water. You have to weigh it on balances. And if you know the mass of the water, you know what time elapsed, what time did it take for this water amount to flow. So Galilei used water clocks to measure time intervals, and he investigated this process of the balls rolling down. And he measured time intervals, and he measured the distances or the displacement of the ball, the distance covered by the ball, or the displacement. So if the ball starts here and then the ball is measured at this point, we can easily measure the distance or displacement of this ball, and we can measure the time interval which is necessary for the ball to go from here to here, from initial point to final point. And Galilei presented his results in such a way that the time interval and the displacement, or the path covered by the ball, were arranged in such a table. So suppose the time interval is unity, and the displacement can also be taken as unity, in whatever units of measurement you prefer to measure the distance. It may be in inches, it may be in a unit may be taken as 10 centimeters, or a unit length may be taken as 20 centimeters, any given unit length, which you can choose arbitrarily in any experiment, and then measure all the distances using this unit. So if the body travels for 2 time intervals, twice the initial time interval, then the distance covered will increase 4 times. If the body travels 3 time intervals, then the distance covered will be proportional to 9 original distances, and etc. And Galilei formulated such a law of motion. In this case, he said that if time intervals form an arithmetic sequence, then the distances covered will form a geometric sequence. In such a way, all the results were presented by Galilei in his works. Newton was born in the year when Galilei died, so they never met, they never discussed physics. But Newton read papers, read works of Galilei, and he was well aware of such results, and Galilei carried out a lot of experiments using different angles of the inclined surface, different distances, and different balls of different masses. That was a considerable investigation of the phenomena involved. The Galilei presented a lot of experimental results. So Newton was aware of these results, and Newton used Galilei's results in order to formulate his laws of mechanics. But very important thing that was noticed by Galilei was the behavior of the ball after it appeared on the horizontal surface. When the ball continues its motion along the horizontal surface, the ball turned out to move with constant velocity. That is, in equal time intervals, the ball made equal displacements. The displacement was proportional, the total displacement was proportional to the time interval, the time required for motion. Galilei noticed this fact that the velocity is constant. And Galilei understood well that there are no forces acting on the ball while the ball rolls along the horizontal surface. Well, actually there are 2 forces, one force of attraction to the ground and another force of reaction of the surface, but these 2 forces are balanced. So all the forces acting on the ball are balanced. The net force or the resulting force is 0. Therefore, Galilei understood that if no forces act on a moving body, then the body keeps moving at constant velocity. In contradiction to the law given by Aristotle, Aristotle said that if force is equal to 0, then the velocity must be equal to 0. Okay. That must be better for this camera. Okay. If force equal to 0, then according to Aristotle, the velocity must be equal to 0. In Galilei's experiment, something different was observed. The force is 0, but the velocity is not 0. The velocity is constant. That's one of the reasons why Galilei carried out so many detailed experimental investigations in order to make sure that Aristotle's formula was not correct in this particular situation. In some situations, this formula works well, and we discussed it. When you are in a boat, you need to apply larger force in order to move with higher velocity. That's quite reasonable when you move something, when you push the cart, when you move any object. We take any object. If there are no forces acting on it, it doesn't move. It doesn't move. But if you want to move it, you have to apply some force. And if you want the velocity to be higher, you have to apply larger force. That's natural. And that result relies on experimental observations. But what Galilei observed was something different. In this particular case, the force was 0, but the velocity was not 0. The velocity was constant. Galilei formulated this observation as the law of inertia. The law of inertia was formulated by Galilei. And he said that if no forces act on a body, or all the forces acting on the body are balanced, then the body keeps moving at constant velocity. Galilei formulated this law, which Newton gave as the first Newton's law. But Newton did not attempt to pretend that that was his law. No, he referred to Galilei, and he referred to his works with great respect. He said that the Honorable Galilei presented his investigations and formulated his law of inertia, which should be put as the basic law of classical mechanics. So Newton referred to Galilei when he formulated this law, and Galilei actually discovered the law of inertia. Also, Galilei understood that the law of inertia is valid not always, but only in inertial reference systems. So you don't, in order to observe the correct inertial behavior of a body, you must be in an inertial reference frame. You mustn't be accelerated. You must be at rest, or you must move yourself with constant velocity. If you move with acceleration, then this law of inertia will not be observed. So Galilei understood that the law of inertia is the basic property of nature, and that the law of inertia holds in an inertial reference system. That is, in a reference system which doesn't, years ago, started the papers of Galilei, studied his works, and formulated his laws. The first law, the law of inertia, was actually formulated by Galilei, and Newton repeated this law as the basic law of mechanics. The second law, as you know, is force. Force is equal to the product of mass of the body and its acceleration. You know, this is the second Newton's law, but actually Newton never used such a formula. Newton never wrote exactly this formula. Newton put it in somewhat different way. We will discuss it, but when Newton formulated the second law of mechanics, he also relied on Galilei. He referred on the results obtained by Galilei. And he said that this law was actually discovered by Galilei, which is not true. Galilei never expressed his, it's not quite true. Galilei presented a lot of experimental results, but he never wrote any formula. Galilei never attempted to write anything like that. So Newton processed the formulas, processed the results of Galilei. What are the results of Galilei? The results are this, that if this is time, then the distance covered by the body is proportional to time squared, which is obvious from the results, from experimental results. So the distance d equals some coefficient of proportionality alpha, t squared. And Newton developed his calculus, and he knew how to differentiate, how to find a derivative. So he understood that if we take a derivative of this formula, if we find a derivative d dot, a derivative with respect to time, then differentiating this formula we obtain 2 alpha t. And if we find second derivative, and that first derivative of displacement is certainly a velocity. But if we find second derivative of displacement, that will be the first derivative of velocity. If we differentiate this function, we will obtain 2 alpha. So this is, as the first derivative of velocity, this must be an acceleration. Therefore, from these results, we can obtain that if 2 alpha is acceleration, then the velocity must be equal to acceleration 2 alpha. This is acceleration time. And the distance covered by the body must be equal. Alpha equals what? Acceleration divided by 2. Acceleration divided by 2 times squared. So Newton understood all these formulas, and he put all these formulas, and he analyzing the results presented by Galilee, Newton actually discovered that the velocity is not proportional to force, as Aristotle had believed, but the velocity is proportional to force multiplied by time interval. And Newton put it in this way, that the velocity is equal to force divided by m time interval, where m is the mass of the body. Why is it true? Because when the ball is on the inclined surface, the force acting on it, that is the force of attraction to the Earth, is proportional to the mass. It's mg. The force of gravity is proportional to the mass of the body. So, but the acceleration of the body does not depend on its mass, as was established in Galilee's experiments. So the acceleration, which is here, that is acceleration. Acceleration should not depend on the mass. It means that if the force is proportional to mass, and acceleration does not depend on the mass, then the acceleration should be directly proportional to force and inversely proportional to the mass of the body, so that the mass cancels here. In this way, Newton actually derived the second law of classical mechanics based on the results presented by Galilei in his many experiments. Now we will demonstrate you the Galilei's experiment. This is an inclined surface, an inclined trough, such that metal balls can roll down. And while the metal ball rolls down, it will touch a small contact here. And when the ball touches the contact, you will hear a click. And the contacts are arranged in such a way that each distance, the next distance starting from 0 is 4 times the first distance. And another distance is 3 times the first. The distance is, if this is 1, this is 4, this is 9, exactly according to this proportion. The distances are related as the squares of natural numbers 1, 2, 3, 4. The distances here are related as squares, and you can see that if this distance is 1, then this is 4, and this is 9. Okay. Now we will try to... Тима, ты сделаешь или я пропущу? В чем проблема? Okay. Here we have a lamp which glows slightly all the time, but when the ball touches the contact, the lamp is switched off for a short moment of time. So if I start the ball from the 0 position, then according to the results of Galilee, no, it doesn't go. Too big. It's too big. Yes. It's too big. А вот поменьше. Шарик. That's it. What he observed, the clicks were made in equal time intervals, like in 1 second. 1, 2, 3, 4. Еще разок. That's it. That's okay. Достаточно. So according to the results of Galilee, we have just repeated this result. You have seen that when distance covered by the ball, when distances are related as squares of natural numbers like 1, 4, 9, 16, then the time interval required to cover this distance is just the time intervals are equal. 1 second, 2 seconds, 3 seconds, 4 seconds, equal time intervals. That's enough. I will switch it off. Okay, such experiments were carried out by Galilei, and he worked for a long time. That was part of his life to investigate this phenomenon. It was not like 2 or 3 days. No, it was for a long period of time. And so Galilei never presented his results in a form of any formula. He presented just like the experimental tables. And Newton processed his results in this way and obtained all these formulas and understood that this is here the ball moves with constant acceleration, and therefore the velocity is proportional to time. The velocity is proportional to time, in contrast to what Aristotle had believed was true. And so Newton arrived at his second law, which is actually based on the results of Galilei. Newton actually never used this formula in his works. He somehow understood that it's necessary, or it's very useful to introduce a new physical quantity, which is a momentum. Newton defined the momentum by definition as the product of mass of the body by its velocity. If we do it in this way, and if we calculate the time derivative of momentum, we will obtain m v dot, which is acceleration, and that should be force. So Newton understood, instead of this formula, Newton used this formula. He already knew that the force is a vector, and he said that this vector is time derivative of the vector of the body's moment, mass times velocity. So Newton put his second law of classical mechanics in this way. I remind you that P vector dot is dP by dt according to Leibniz notation. This is the Leibniz notation, and this is Newton's notation. That's the same thing. Sometimes we use Leibniz notation, which is sometimes it's more convenient, and sometimes Newton's notation is more convenient. So we will use both notations. It's a surprising thing. It's unbelievable, but Newton used exactly this way to express the second law of classical mechanics, and this formula turned out to be correct both in special relativity and in quantum mechanics. While this formula is certainly incorrect in special relativity, it cannot be used, and I will just make a short remark on this issue. In special relativity, French physicist Poincaré obtained this result because he was working on special relativity at the same time when Albert Einstein did. And Poincaré found that an electron in electromagnetic field obeys the following formula, that the force acting on an electron at any velocity of the electron is related to the acceleration in the same way. It's not merely mass times acceleration. It's mass acceleration divided by square root of the velocity squared by c squared, the velocity of light. Such a formula is a consequence of Maxwell's equations describing the electromagnetic fields and the behavior of charged particles, motion of charged particles in electromagnetic field. At first, people were about to believe that the mass is a function of velocity. The higher the velocity, the higher the mass. The closer the velocity of an electron to the velocity of light, the larger should be the mass of the electron. That was the first intention. That was quite natural. But later, it turned out that such an approach leads you nowhere. Because if the electron moves in this direction, and the force, this is the velocity, and the force acts at some angle, then the acceleration of the body will be directed at some other angle. The acceleration will be here. And therefore, we have to introduce the longitudinal mass along the direction of the velocity, and transverse mass, which is perpendicular to the velocity. This is a mass. This is a confusion. The mass of the body appears to be some tensor, some matrix. And the tensor, the mass, like a tensor, does not obey the usual tensor laws of transformation of coordinate system. So this is a mass. If you go along this way, if you believe that mass depends on the velocity, then you will have to agree that there is one mass, very high mass, which is the measure of inertia of a body along the velocity vector, and another mass which is perpendicular mass. The inertial properties of the same body in perpendicular direction will be different. The perpendicular mass will be much smaller than the longitudinal mass, the transverse mass. So we come to a conclusion that there is not a single mass of the body, but two masses, one longitudinal, another transverse mass. And these two masses do not obey in a reasonable way. So this is a mess. This is a confusion. And so people came to a conclusion that the mass of the body does not depend on the velocity. It's a constant property of a particle. It's a constant property of a particle. And we have to use this formula, that we have to use the Newton's second law in this way, written here, connecting the derivative of time derivative of the momentum with the force. And the the time and the momentum of the particle will be given by mv divided by 1 minus v squared over c squared. So if you use this formula together with the second Newton's law, then everything will be okay everything will be all right in relativistic calculations. Also in quantum physics, to calculate the momentum of a particle, it's not an easy procedure. In quantum physics, the state of the particle is given by a wave function, which is a complex function of the particle coordinates, and the wave function occupies all the space, actually. And in order to calculate any physical quantity, you have to use the quantum operator related to this quantity. It's not merely a number, it's an operator. And in order to calculate the average value of any physical quantity, you have to take an integral over all the space, and under the integral you will have a wave function complex conjugate, then operator of the corresponding physical value, then the wave function again, and all this expression should be integrated over all the space. So this is not a trivial procedure in quantum physics, but if you follow this procedure and calculate the average momentum of the particle according to quantum rules, then you will discover that this law holds even in quantum physics, with the only reservation that the momentum should be calculated according to quantum laws using quantum operators. So the formula given by Newton turned out to be superb and applicable both in relativistic physics and in quantum physics. And Newton never wrote this formula as it was given to you at school. But for school children, this is okay. This is a primitive way to formulate the second law of classical mechanics, which we call Newton's law. But Newton himself said this was Galileo's law because Newton relied on Galileo's results when deriving this formula. 5 minutes break. So we continue after this short interval, consideration of Newton's laws. And you certainly know well the third Newton's law, which Newton discovered when he considered gravitational interaction between different bodies. The bodies with gravitationally interact with the Earth, and the Moon is gravitating with the Earth, interacting with Earth, and all the planets are interacting with the Sun. All these are gravitational interactions, and Newton spent a lot of time to study the gravitational interaction. And actually, in order to understand the gravitational interaction, Newton developed his calculus in order to be able to solve different problems related to gravitational interaction. The calculus, the differential and integration differential and derivatives and integrals, all this was developed by Newton to be able to solve different problems. And when considering gravitational interaction, Newton formulated the third Newton's law, which you know well. If we have two bodies of masses m1 and m2, then the force acted on the first body, F1, by the second body. I will denote such a force as F12. That is the force acting on the first body by the second body. Should be equal in magnitude to the force acting on the second body from the first body. So these two vectors, F12, should equal to minus F21. Newton discovered this law while solving problems in gravitation, on gravitational interaction. So this law involves several important points. First of all, the two forces of interaction are applied to different bodies, and therefore they don't balance each other. They are applied to different bodies. Second, these two forces are equal in magnitude, and they are oppositely directed. And there is another very important point about this Newton's third law. The two forces are directed along the same line. It should not be in this way if one force is directed here and another force is directed here. So it can be such vectors F12 and F21 may be equal in magnitude, and they may be directed, have different directions, so that this is true. This requirement is satisfied. But if these forces are aligned along different lines, not along the same line, then that would be a pair of forces which would turn out to rotate the two bodies, and the two bodies will start rotating quicker and quicker. That never happens in nature. That never happens that the two bodies start rotating with acceleration. No, if they're rotating like Moon rotating about the Earth, or Earth is rotating about the Sun, this rotation goes on with constant angular velocity without appreciable angular acceleration. So the two forces must be directed along the same line. They should not be directed in this way. They should be along the same line. That's another important point about the Newton's third law. And there is Newton's fourth law. Do you know what is it? Newton's fourth law. Have you ever heard about it? You don't know what is it? You do, you know. This is the law of universal gravitation, also discovered by Newton. The law of universal gravitation. It's also Newton's achievement. So when considering the law of universal gravitation, I don't even write it down, you know it very well. When Newton studied this gravitational interaction, he came into conclusion about the existence of this third law of classical mechanics. So Newton himself developed the third law and the fourth law. That's entirely Newton's, to his credit. He discovered these laws. But as far as the first and second laws, Newton himself said that these laws were discovered by Galilee. And Newton just formulated these laws and put these laws into formulas. Newton's third law is not absolutely accurate. You know why it's not absolutely accurate? It will, in many situations, it will give you an error. It's an approximate law. Why? Do you know? Who can tell me why this is an approximate law? Because if you take this mass point and move it very quickly to some other position here, then this mass, after being displaced, will experience different force, F21. It will be different force, I say tilde, but the force acting on the first mass will remain the same for some period of time, until the gravitational interaction covers this distance and the gravitational wave comes to this first mass. It will have no information that the second body was moved or shifted away. The information about the change in position of one body will come to another body not instantly, but during some time interval. And during this time interval, the force acting on the second body will be directed here, and the force acting on the first body will be directed here. They will not be directed oppositely. This third Newton's law will not hold. It will not be true. It will be violated during some short period of time that is required for the gravitational wave to move from one point to another. And gravitational wave propagates with the velocity of light. I say this is a short period of time, but what kind of time or time interval? How much does it take for the gravitational wave to go, for example, from the Earth to the Sun? How much time will it take? About 10 minutes. About 10 minutes, because gravitational wave goes with the velocity of light, and it takes about 10 minutes for light to go from the Sun to the Earth. Such is the distance. So when I say for a short period of time, it means sometimes minutes and even hours. Minutes and many minutes. And sometimes even hours. So this law will not be correct during considerable time interval. Many, many minutes and sometimes even hours. So this is an approximate law, and one should always keep in mind that this law is not absolutely correct. Sometimes when the bodies involved move quickly, then this law may not be correct. Also, the fourth Newton's law, the law of universal gravity, the gravitational interaction, you know, the gravitational force is inversely proportional to the distance between the bodies. But if you have shifted one body quickly to some other position, the distance will change, and the force acting on this body which has moved will change, but the force acting on the first body will change later after some time interval required for the gravitational interaction to propagate with the velocity of light. So for some minutes, this Newton's law of universal gravitation may be violated. That's because of a finite speed of propagation of interaction. Now we consider a closed system of particles. Let's consider a closed system of particles. So let's take particle M1 and particle M2 and particle M3, etc., etc. There may be many, many particles, and one of the particles will be denoted by particle mk, particle m number k. So there are many particles, maybe 100, maybe 1,000, maybe more, maybe 1 million, a lot of particles. All of them are somehow interacting with one another. There is a force acting on the first particle from the second particle, F12, and force acting on the second particle from the first particle. And also forces acting between all other particles. And also there is a force acting on particle number k, Fk, from the first particle, and a force acting from the kth particle, Fk1, on the first particle, etc. All sorts of forces acting between different particles here. I don't have to show all the forces, but you can easily imagine that every two particles interact with each other. In this case, the second Newton's law will be written in this way. The momentum of the kth particle, dot, that is time derivative of momentum, equals the force acting on the kth particle equals the total force. I would put it like this: the sum of all forces, acting on this kth particle from all other particles, all other particles. Let the total number of particles be denoted by capital N. The total number of particles, it may be 1,000, it may be millions of particles, whatever number you choose in different situations. The number may be different, but we denote the total number of particles to be capital N. And so the change of momentum of particle number k, the rate of change, that is the time derivative, should equal the net force acting on particle k from all of the other particles. So I have to find the vector sum of all forces acting on particle k. You understand what this symbol means? It means that I have to calculate the vector sum fk1 plus fk2 plus etc. plus the final fkn capital. All the n capital particles act on our particle number k, and I have to find the net force. And in order to simplify this expression, in order not to write down all the forces, I use this symbol as sum, the sum of all forces. Now I will like to find this equation applies to any particle. K may be equal to 1, or 2, or 3, or capital N, whatever, any particle. So now I will write down all these equations for all other particles. For particle 1, the same. For particle 2, for particle 3, for particle N, the same. The same equations for every particle. And then I will find the sum of all these equations. I will sum all these equations. I will add them. So I will obtain the sum of all momenta with the dot, that is a derivative, time derivative of the momentum of particle number k I will sum from k to capital N equals the same sum from k 1 to capital N of this expression. And this expression is the sum from small n equal 1 to capital N. And here we have force Kn, force vector of force. So here, first I have to sum up all the forces acting on particle, given particle number k, from all other particles. And then I sum up all the forces acting on all other particles. In this total sum of all the internal forces, for any two forces k, j, there will be a third Newton's law, which can be written in this way. The force acting on the k's particle from the j particle will be equal to the force acting on the j particle from the k particle. And from here, I obtain that for any two particles, force Fkj plus force Jk equals 0. For any two pair of forces, the sum of their vectors is 0. It doesn't mean that these two forces cancel each other. They cancel each other algebraically, but in reality, they continue acting, and they are applied to different points, for example, to different planets. And these planets continue their motion in accordance with the forces applied. So these forces actually can act on each particle. But mathematically, they may be cancelled in such a way. And so I obtain that if any two forces here cancel, then the whole sum equals to 0. And it means that from here I obtain that the sum, I will put it in using Leibniz notation, dp k over dt. The derivative is such an operation. It's a linear operation. It means that the sum of derivatives equals the derivative of the sum. So I take the d over dt from the sum, and here I obtain the sum of all momenta. And the sum of all momenta is the total momentum of the closed system. Total momentum. Total momentum of all the particles. Total momentum. And we have come to the conclusion that this total momentum derivative with respect to time equals 0. This equals 0. The time derivative of the total momentum equals 0. And from here we come to the conclusion that the total momentum of the system of particles remains constant. Because if you take time derivative of the constant, then you obtain 0. And that's what we have here. Time derivative of this vector is 0. It means that the vector itself remains constant in time. It doesn't change in time. That is the law of conservation of momentum for a system of particles, for a closed system of particles. What does it mean, closed? Closed system, as we considered here, is such a system of particles which interact only between each other and don't interact with the outside world. No outside forces act on this system of particles. Such system of particles is called closed. So we obtained the law of conservation of momentum for a closed system of particles. To obtain this law, we used and relied on the third Newton's law. And we have just discussed that the third Newton's law is not very accurate. Sometimes it's violated. Sometimes it will give you an error. It means that the law of conservation of momentum is also not very accurate. It should also produce some error sometimes. In Newtonian times, that is about 300 or 200 years ago and 100 years ago, that question was not well understood. People did not quite understand whether the law of conservation of momentum is a precise law of nature or if it may be some approximate law of nature. And that situation of uncertainty continued until the beginning of the 20th century, when a German scientist, Emmy Noether, she proved a theorem, a very important theorem. She was a mathematician, a German mathematician, and in the beginning of the 20th century, she proved a very important theorem. She proved that the law of conservation of momentum can be derived from the fact that our space is uniform. It means that any physical experiment carried out in this volume of space will give you the same result as the same experiment repeated in another volume of space. So these 2 points in space are equivalent. Nothing changes if you move from one point of space to another point of space. All space volumes have the same properties, and all physical experiments will produce the same results, whether you set up this experiment here, or you set up in another corner of this room, or you set this experiment in another laboratory or on another planet. It doesn't mean, it doesn't influence the results. All the space points are equivalent. It means that the space is uniform. And from this uniformity of space, the law of conservation of momentum can be obtained. Actually, Emmy Noether proved that a law of conservation of some physical quantity must hold every time there is some symmetry in your system. If there is a symmetry with respect to translational symmetry, translation in time, then you will have a law of conservation of momentum. If you have a symmetry with respect to translation in time, not in space, but in time, it will give you a law of conservation of energy. If you have a symmetry with respect to rotation, meaning that all the directions in space are equivalent, you may set up an experiment with such orientation, and you may rotate it and turn it by some angle, and the result will be the same. All the directions are equivalent. It means that there is a symmetry with respect to rotation. That symmetry produces inevitably a law of conservation of angular momentum, etc., etc. Any law of conservation is intimately related to some symmetry in physics situation, in physics law, in physics experimental situation. So any symmetry produces a law of conservation. And based on this result of Emmy Noether, people understood that the law of conservation of momentum for a closed system of particles is not an approximate law. This is a totally correct law, because the symmetry is absolute. The 2 points in space are absolutely equivalent. And therefore, this law is absolutely correct. How can it be related to the fact that the third Newton's law is not absolutely correct? This is not precise law, but based on this law, we derived absolutely precise law. How can it be so? How can it be so that based on the wrong assumption, actually, we obtained correct consequence, correct result? How can it be so? Well, think about it. It may be a good question for a question of choice, for example, on your exams. If you choose this question of choice to explain it, how can it be that based on a wrong assumption, we obtain absolutely correct result. How can it be so? If you succeed in clarifying this problem, that will be a good question of choice. Anyway, a law of conservation of momentum is absolutely correct because of the Aminota's theorem. Another thing I wanted to discuss today is the integration of second Newton's law. So, second Newton's law can be put in this way. Acceleration is a force, vector of force divided by m. But acceleration is the first derivative of velocity. And velocity is the first derivative of coordinate. So this is a vector of coordinate second derivative. In Newton's notations. In Leibniz notation, this will be written as d2 of vector r over dt squared equals vector f over m. That's in Leibniz notation, and the first line is in Newton's notation. The same thing in different notations. So, if this is actually this is a differential equation. We have coordinate r, a vector, radius vector, pointing at some particle. And if we want to know how this particle moves, we actually are interested in the function r of t. Radius vector is a function of time. That's what we have to obtain. How can we obtain it if we know only this law of nature? The second derivative of vector of r is known, while f may be some function of time. So this is a differential equation, and in order to solve this differential equation, in general case, we have to integrate it. Well, after integrating first time, we will obtain after integrating the first time, we will obtain the first derivative of vector r as a function of time. That's the velocity as a function of time. And certainly, when we integrate an equation, if you know anything about integration, you understand that when we integrate, we inevitably obtain an integration constant, some undefined constant, which is the result of integrating. If we integrate the second time, we obtain the required function r of t, and it will be given as some function of time and the first non-defined constant and the second non-defined constant as the result of the second integration. Each integration gives you some constant, non-defined constant. So actually, we may integrate this equation in general case, and we will always obtain some function of time for this radius vector, how it changes in time, but the function will be not quite defined. It will contain some constant, two constants, which we don't know. We don't know what are these constants equal to. These are non-defined or undefined constants. What should be done in order to define these constants? Actually, if you go from one quantity, from one value for the first function to another value, and from one value for the second function to another value, if you shift these values of these functions, you will shift the trajectory. And instead of a single trajectory, you will obtain one trajectory for one value c1 and another trajectory for another value of c1. So this is the first trajectory, second trajectory, etc. You may obtain many trajectories many trajectories. Which trajectory should you choose? And each trajectory corresponds to certain values of these constants. Which trajectory should you choose? As a matter of fact, when you solve any mechanical problem, you know well the initial conditions, the conditions of a system at the initial moment of time. At the initial moment of time, you know the position of the particle, that is r, at the initial moment of time when t is 0. And also you know the velocity of this particle at the initial moment of time. So actually you know the initial position and initial velocities. And so these initial positions, two equations are necessary, two equations. That is, for t equals 0, we have to know the vector, the initial vector, the initial position of particle, and we have to know the initial velocity of the particle, v0. If we know these two quantities, if we determine the initial position and the initial velocity, then we can find these two unknown constants by solving these equations, by substituting this formula into these initial conditions. By substituting here, you can solve this system of two equations in order to find two unknown quantities. You can always find two unknown variables if you have two conditions, two equations. So in order to solve the second Newton's law in any general case, you have to integrate the second Newton's law. You have to integrate this differential equation. And when you integrate it, you inevitably obtain two constants which are unknown to you, but which can be defined if you establish the initial position for this moving particle, the initial position and the initial velocity. So the initial conditions will always allow you to solve the second Newton's law as a differential equation. This final remark concerning the laws of classical mechanics, the Newtonian laws, well, it's just a general consideration for the general case, and whatever particular problem you solve, you will, in many cases, you will run across some unknown constants which can be defined using the initial conditions. That's a general considerations. In the end of this lecture, I wanted to tell you one thing which I believe is important. You have entered this university for a bachelor's program, and you will study for 4 years, you know. And during the first 3 years of your studies, you will have practically no classes devoted to your specialty. If you are specialized in aerospace technology, aerospace engineering, or if you're specialized in biomedical engineering, you will discuss these special courses in your specialty only after 3 years of studies. And during the first 3 years, you will study only physics and mathematics and some other fundamental sciences. That is because in order to understand the modern technologies, you have to know a lot. You have to know mathematics. What does it mean to know mathematics? It doesn't mean to know algebra or trigonometric functions. It means that you should know calculus, how to differentiate and how to integrate functions you should know. You should know theory of probability. You should know linear algebra, which is widely used in quantum physics and in computer programming, in different algorithms. Linear algebra is very important. And you have to know many other mathematical sciences. You have to acquire a good deal of mathematical knowledge. Also, in physics, you have to obtain a fundamental understanding of general physics in order to be able to understand modern technologies. So it would be senseless to teach you your specialty today, because you have no fundamental education in math, no in physics. First, you have to obtain fundamental knowledge in basic sciences, in physics, mathematics, and some other subjects before you are able to learn modern technologies. That's why for the first 3 years you will learn practically for 99% practically only the basic and fundamental sciences, not your special subjects. And also when you will begin to study your subjects, your specialty, you must understand one simple thing. For example, if you study aerospace technologies, you should understand that there is no single person on this planet who knows everything about the space rocket. Nobody knows how it works, because space technology or space rocket, for example, it involves a good deal of information, a huge information. First, it's information on materials, which alloys to use, which composite substances, composite materials to use in different situations. So there are hundreds and thousands of people who devote their whole lives to studying materials and their properties in order to use proper materials for a space rocket. Another thing, apart from materials, you have to know, some people study structural safety or structural stiffness. The stiffness of a structure. So in order to obtain a rocket which would be very, very stiff and very reliable, it must have thick walls, it must be very strong, very sound, but it will be very heavy. It will not fly. If you want to make a rocket light enough, not heavy, to be able to fly, then the walls should be made thin. And the thinner the walls, the more flexible is the structure. And the structure stiffness is very important. So there are hundreds of people who study this subject, and they use computer software to simulate all sorts of structures in order to find the proper structure for a space rocket. Also, there are many people who devote their lives to study chemical studies in rocket fuel, because you have to choose the proper fuel and proper oxidizer for this fuel and proper conditions for its manufacture and proper conditions for its storage and maintenance. So hundreds and thousands of people devote their lives only to fuel problems. Also, there are many, many people who study and investigate, many engineers who investigate the issue of pumping the fuel into the combustion chamber of the rocket. How to pump the fuel? It will not flow by itself, because the pressure in combustion chamber is very high and no liquid will flow there by itself. You have to pump this liquid with heavy pressure, with large pressure. And so how to pump liquid? How should be the pump constructed, and what energy should this pump use to pump the fuel into the combustion chamber? Hundreds of people are engaged in these investigations, engineering calculations. Also, there are people who study systems of automatic control of the rocket flight. When the rocket flies, it must be automatically controlled how it goes, along which trajectory it goes. There are people specializing in the systems of automatic control. And also there are many, many people who are engaged in life-sustaining equipment, so that cosmonauts or astronauts there should be able to sustain their life. They should have fresh air, and they should have fresh water, and a good temperature, not very high, not very low. So many, many people work on this issue. And there are many other issues involved. And each small problem, small topic, requires hundreds and even thousands of engineers and specialists and scientists working on it for years and for dozens of years. Can you know everything? No. Nobody is able to know everything about the space rocket. No, there is no single person on Earth who knows everything about the space rocket. So if you study space engineering, don't think, please, that you will know everything. No, you will know, probably you will have some general concept about everything, just some general words. And then you will have to specialize in some particular engineering subject, in some particular problem. That's the purpose of your studies here, as far as I understand it. Okay, we had a bell, and that's the end of our lecture. Thank you, and goodbye till Wednesday.